Do you have any questions for me, guys, before we start? I take it as a no. Okay. And as always, I'll start sharing my screen where I have a few problems. Do you have questions, Will? I see that you are laughing. Okay. No? Are we sure? You can ask anything. No. Okay. Okay, so let's get started. And I know it's late. I know you are tired and you've had a very long day. So I'll keep this session as short as I can. Okay, guys? Okay, so let's get started. Okay. Now you should see. Okay. Do you all see my presentation, guys? All good?
Yep.
Okay. So I promised last time that we would start with an exercise on a specific reaction that we did not cover on Tuesday. So here is this problem about this reaction. And what I would like you to tell me, guys, is how we can synthesize this compound enantiomerically pure. And we can start from these starting materials. So from this allylic alcohol here and this other compound here. So how can we proceed, guys?
Is this the sharpless asymmetric epoxidation?
It is, Will. Excellent. So what do we epoxidize here? What do we do?
You'd want to epoxidize the double bond in the left-hand side molecule.
Okay, that's correct. And something to note about this epoxidation is that this specific reaction only works on allylic alcohols. Okay, guys? So for this reaction, we need to have our double bond, a CH2 group, and a OH. So the double bond can be substituted, no problem, but it has to be an allylic alcohol in terms of the substrate for the reaction to work. Okay. So what do we do, guys? So considering we have our starting material, we said we want to make an epoxide of this compound. Let's look at the configuration of the chiral centers in the final product. So considering that, which epoxide do we want to make, guys?
A wedged one.
So is the oxygen coming towards us?
Coming towards us.
Coming towards us. Very good, Jack. Excellent. So can you tell me what do we need in the reaction in order to get this epoxide here, guys?
D minus diethyl tartrate.
Excellent. Very good, Jack. So here I have given you this little reminder of a general rule that we can use in order to understand which enantiomer of the diethyl tartrate we need to use in order to obtain the desired epoxide. So we always orient our allylic alcohol in order to have the OH group top left, and then once we are in this situation, we decide which enantiomer of the diethyl tartrate we want to use in order to get the desired outcome. Okay, very good. So from here, what do we do, guys?
So you just have the nitrogen act as a nucleophile.
Yes, very good. Very good. So which reaction is that, guys? Is it an SN1 reaction, an SN2 reaction?
SN2.
Yeah.
SN2, very good. So we will probably need to remove the proton from here in order to have a good nucleophile. Okay. So can you draw the curly arrows for me, guys? And you should be able to annotate. Yes, you are able to annotate. Where does this N- attack?
Oh, this there.
Mm-hmm. So here, yeah.
So I was going to go there. That's going to
Okay,
go there.
very
Then that's going to like protonated or whatever.
excellent. Okay, so we have that the attack happens at the benzylic position because it is more reactive, okay, when we have the benzyl group there, and we have the curly arrows exactly as Will has drawn. Okay, very good. Now we have this nice intermediate. What can we do, guys? Let's look at the structure of the final product. What would you do? So we have created this situation, an hydroxyl group here and a nucleophile, let's call it this way, on the other side of this CH2CH2 using an epoxide. What can we do to obtain this kind of situation on this side of the molecule, guys? So when you see hydroxyl groups, CH, CH2, or even with a substituent, and then a nucleophile, it should ring a bell for something. Something that we have just seen.
Another epoxide.
Another epoxide. Excellent. How would you make it from here? So we can make another epoxide, and then we can open it with what, guys?
Do we do another sharpless or?
Okay, in this case, we don't, because we already have the hydroxyl groups in place. Okay, so what we can do is to convert our dihydroxyl situation into an epoxide, making this OH attack and kick something out on this level. Okay, guys? So one way we can do this is to use tosyl chloride. Okay, so we create a good leaving group on the level of this alcohol here, and the tosyl chloride will only react here because it is less hindered, this position. So now we have a nice leaving group here. What can happen, guys?
So now the oxygen on the alcohol can attack the carbon and the OTS can leave.
Yes, that's it. What do we do though for this oxygen to attack?
Deprotonate it?
We need to deprotonate it. Very good. So we can use sodium hydroxide, for example, and we can deprotonate this OH. Okay, guys? So very quickly, we have the OH minus from the sodium hydroxide that removes this proton. And now we have the attack at this level and we kick out the tosylate leaving group. Okay? And we obtain a second epoxide. Okay? I need to clear the annotations now. Clear all drawings. Okay, from here, what do we do? Let's look at the structure of our final product.
So
methyl. Do we have to do like N3 or is it just methylamine?
Methylamine will work just fine. So we can use methylamine, which will open our epoxide, attacking at the less hindered position in this case. And here we have our nice final product. Okay, guys? So the sharpless asymmetric epoxidation is a super important asymmetric reaction that we need to keep in mind. And it is very important also that we remember it works only on allylic alcohols. Okay, guys? Okay. So now we move to another asymmetric reaction that we have encountered instead in the video for today. And I've made your life very easy in this slide because I've used the reaction we need as a title for the slide. Okay. And it was a mistake. I don't know how I can have done something like that, but I did it. Okay, so what would be our starting point here? We want to synthesize this compound.
So we need an alkene?
Yes,
For...
so we need an alkene. Instead of having the two hydroxyl groups, we start from an alkene. Now, for this reaction, you have seen in the video that we want to have the substituent groups on our alkene in a certain position in order to understand which ligand we have to use. Okay, so if we want to understand the ligand to be used, guys, what can we do with this alkene here?
So it's largest on the left, smallest on the right.
Exactly. So we need to redraw it, okay, guys, because we want to have this situation. We want to have our double bond in the middle, the largest group always bottom left. If it is possible, the next to largest group top right. Okay. So now, guys, what do we do? Which alkene do we make from this situation here?
The SS one. Oh, that's one, but never mind.
Do we want now from this situation here, guys? Do we want the hydroxyl groups to point towards us or away from us?
Away.
Are you sure, guys? Look, if
oh no, because we've redrawn it, haven't we?
Exactly,
So
we have redrawn it. So if they point away, we would have, if we imagine a symmetry plane here, so a mirror, if they point away from us, we would have the mirror image of what we have here, right, guys? So if we have the mirror image, it means we have the other enantiomer, correct? Are you with me?
Yeah.
Yeah?
Yeah.
So where do we want this hydroxyl to be, guys? Pointing?
Coming towards us.
Yeah, now
towards us, okay? And it is the RR. That's fine, no worries. Okay, so in order to do that, the conditions of the sharpless dehydroxylations are the same. We just need to change the ligand that we use. So when the alkene is in this position, we want to use DHQD in order to have our hydroxyl groups delivered from the top face of the alkene. Okay, guys? If we redraw this molecule here, we see that it is exactly the same enantiomer that we wanted to start with. Okay? Okay. Are we all good so far, guys? Yeah?
yeah.
So the conditions, so it must be at 0 degrees for this to happen, or?
Yes, so yes, we want for the conditions, this reaction is performed at 0 degrees, okay, Albor? So this year the exam will be open book, so there wouldn't be any need for you to memorize anything because you will have your notes available, okay?
Is that due to it being a kinetic product, or is that just the condition?
No, it is the reaction, how it works, okay?
Okay.
Okay, guys, so now we are always discussing the same reaction, but how can we make this compound instead?
So do we have to epoxidize this one?
No.
Oh.
I don't think so, no. Interesting.
It's the same reaction, so it will be a dihydroxylation.
Oh, so this is when you would add SO2 Cl2. So you want to cyclize it, or?
No.
No. Wait, what was it again?
I'm actually looking at a completely wrong thing.
Yeah.
Maybe an option, but in this case, I would like you to see something else. So these two guys here, they look in opposite direction, right? So they don't look like they come from a syn hydroxylation, correct? Is there a way we can redraw them so that they are in the same direction, guys?
Could you keto-eno tautomerize it?
We can rotate around this bond, correct? And it will be the same molecule.
So
So
we
if
can
we
both
rotate
fake
I
around
see.
this bond, what do
Yeah.
we get?
Ah,
We get this situation.
that makes
Okay.
sense.
And then you can have a cis double bond.
Excellent, very good. So we can have a cis double bond. Okay, guys. Once again, we have our largest substituent, bottom left. Okay. So we still want our hydroxyl to be delivered from the top face. Okay. So also in this case, sharpless asymmetric dihydroxylation, and we still use this ligand, which will make our hydroxyl groups be delivered from the top face. Okay.
So is those conditions like almost all exactly the same with
conditions? Yes, Albert, same conditions. The only thing that changes to give you a different outcome is the ligand, okay? The chiral ligand, okay? Same conditions.
Sweet.
Okay, can I move or shall I wait a second longer, guys? Am I
Yes.
good to go?
I think so, for me at least.
Okay, that's good. Okay, now guys, only one quick breakout room for today. And I would like you to think about two ways in which we can obtain this compound, okay? I'll give you the starting point. So it's again a double bond. And I would like you to tell me two ways in which we can achieve this result. So I can tell you that one way is using a reaction we have seen for Tuesday. The other way is using a reaction we have just seen, okay, guys? But in that case, it will be in 2 steps, okay? So I'll stop sharing my screen. And as always, I'll try to send you the right file in the chat. Let's see if I manage to mess everything up. So, should be this one, breakout room, open. Okay, so if you can, please, guys, check that you can download the file and it is the correct one.
Yeah.
Yeah, it's
The correct one, right? Now what I have done, I don't know. Okay. Okay, so we have the right file. I'll divide you into breakout rooms. And how many are we? 21. So I'll make 6 breakout rooms for today. And yeah, small groups. And I will give you, so this exercise shouldn't be too long. So I'll give you 6 minutes only this time. Okay, guys? So I'll see you all in...
So can we just